So let me ask you this. Will H plus react with hydrogen? So H plus wants to take 2 electrons from hydrogen. If it takes 2 electrons from hydrogen, what do we form? So in other words, if H plus reacts with hydrogen, we're going to form hydrogen and H plus, the same thing. So no change, no reaction. And therefore, in order for H plus to react, we need something stronger than hydrogen. What's stronger than hydrogen? What? Lead. Is lead stronger? Yes. The strongest is lithium. And so as we go down on this side, it gets stronger and stronger. As we go up on this side, it gets stronger and stronger. So it'll react with lead. When H plus reacts with lead, what do we form? Yeah. So if H plus reacts with lead, we're going to form lead 2 and hydrogen gas. So going from H plus to lead 2, we're going from stronger to weaker. When H plus reacts with tin, what forms? Tin 2 and hydrogen. So we're going downhill on the left and we're going downhill on the right, although it's uphill. When H plus reacts with iron, what forms? Iron 2. So that's favorable. We're going from stronger oxidizer to weaker. And this likewise on the reducer. We're going from stronger reducer to weaker. When H plus reacts with zinc, what forms? Zinc 2. So stronger to weaker. These are all downhill. And hydrogen gas. We call all these the active metals because they can react with acids like HF or other mineral acids to form hydrogen gas and metal cations. Yes. And so eats away or dissolves the metal from solid to aqueous. And so HF will react with all these. Or H plus, I should say. H plus will react with all those. And there's going to be some H plus. So weak acids partially dissociate. And so there's some H plus there that can react. So what we say is H plus oxidizes all reducers stronger than hydrogen gas, such as lead solid. All right, H plus occurs on the oxidizer side. Fluoride occurs on the reducer side. So what will fluoride react with? So take a look at the chart and tell me what it reacts with. Will fluoride react with fluorine? If fluoride and fluorine react, what forms? Same thing, so no reaction. So what we need is a stronger oxidizer than fluorine. What's a stronger oxidizer than fluorine? There's nothing on the chart. So fluoride's extremely unreactive in redox reactions. It could be very reactive in other reactions, but in redox it's not. Because there aren't that many oxidizers. In fact, there are no oxidizers stronger than fluorine on this chart. Are there any oxidizers that are stronger than fluorine? It turns out, yes, in the universe there are stronger oxidizers than fluorine. They're just not very common because, one, they're super reactive, and two, there just aren't that many of them in type and variety. And so fluoride, what we can say is fluoride reacts or reduces. A reducer reduces, oxidizers oxidize. And so Fluoride reduces oxidizers stronger than fluorine. Well, what's stronger than fluorine gas? Nothing on our chart. And so I'll have to give you a more exotic example. A more exotic example is there's a stronger oxidizer than fluorine. It's called alpha radiation or alpha particles. Alpha particles are extremely strong oxidizers, stronger than fluorine. And what makes them so strong is their helium. Alpha particles consist of helium atoms, but they're helium atoms that have lost all of its electrons. And so it forms a helium-2 plus cation. Helium-2 plus cation is extremely unstable. It wants those electrons back, and therefore it's a powerful oxidizer. These are alpha particles. There are a couple of key differences between redox. You know, the chart's very similar, right? The acid base and the redox chart. But there's some key differences here. When we do, oh no. Let's see. Okay, it's just some news. When we do Bronsted reactions, we only transfer one H plus per reaction step. An example of this would be like phosphoric acid. H3PO4 has 3 acidic hydrogens, and hydroxide is a strong base. And so what we do is we just do this one step at a time. This would form HPO4, H2PO4 minus, plus water. Then this would be step 1. We could do multiple steps here. Step 2, we could take the next proton off. Versus metathesis. In metathesis, we go to completion. In fact, go to completion just means react all the H's. And so if I have H3PO4, I'm going to react all 3 of them with 3 bases, 3 sodium hydroxides. And this is going to make sodium phosphate, Na3PO4, and 3 waters. And so for Bronsted, we only do 1 proton transfer at a time and then reevaluate each time. For metathesis, we'll do all 3 protons. We're going to lose all of them. Let's just make life simpler. It's not metathesis, it can't. Metathesis is going to happen one at a time, but usually when we do it, we just react it to completion. We don't go step by step, like in Bronsted, in predicting products. The other thing to be aware of is acid base is only 1 proton at a time. In redox, we could have 2 electrons. Do you see 2 electrons, 2 electrons, 2 electrons, 2 electrons, and then 5 electrons? 2 electrons, 2 electrons, 6 electrons, 2 electrons, 4 electrons. No particular pattern. There is a pattern there, but it's a bit trickier to see. 10 electrons, 2 electrons, 3 electrons, 1 electron, 1 electron, 2 electrons. And so it's not like Bronsted. Bronsted is very simple. Only 1 proton's transferred. In redox, we have multiple electrons transferred. When we have multiple electrons transferred, then there could be a mismatch. Let's say one wants 1 electron, the other gives up 3 electrons, so there's a mismatch, and we have to balance out that mismatch. With bronzed acid base, we don't really have to worry much about balancing. But for redox, we do have to worry about balancing. What if one wants to give up 4 and the other wants 3? It's a mismatch. But it's easy to fix by cross multiplication. And so here, the number of electrons transferred isn't restricted to 1. We have more than 1, 2, 3, 4, 5, 6, etc. All right. Today we're going to work with silver ions. One of the things we have to worry about silver is a pretty decent oxidizer or a pretty decent reducer. Do you see silver here? It's a pretty decent oxidizer. It can oxidize a lot of things. A lot of things you don't want it to oxidize. Like it can easily oxidize the skin on your hands. In fact, Chem 4, many years ago, I had a student come up to me after lab in a bit of a panic. And she told me she's been washing her hands for like 15 minutes, but the black stains aren't coming off her hands. She had black stains all over her hands. And I thought, oh yeah, okay, those aren't going to come off. Those are, you know what those are? Those tiny, tiny crystals of silver embedded in your cells there. Because when silver oxidizes your skin, it takes electrons from your skin and precipitates out silver metal. And those tiny crystals of silver look black. And they don't wash off because they're not on the surface. They're actually inside your cells, I think. And so I told her that she's going to have to wait, a few weeks for the skin to die and shut off. But she said she can't because she has a very important job interview right after her lab. And I thought, oh no, that's really too bad because, yeah. Anyway, so you want to be careful when we work with silver nitrate. It contains silver ions, and it's going to cause a redox reaction with your hands. It could also cause a redox reaction in your eyes. Fortunately, she didn't get any in her eyes, but if you did get it in your eyes, I don't know how fast do the cells in your eyes shed, or do they, or what? Regenerate all the time? Anyway, it would be bad news if you get it in your eyes. I think it could potentially cause permanent damage. And so be careful with the silver nitrate. Other than that, most of the other stuff is okay. So what we're going to do here is, were there any questions on this? Does this make sense? Oh, actually, we didn't finish it because if I want the chemical properties of HF, then I looked at the acid-base properties. I looked at the redox properties. I should also consider the metathesis properties. And so we're going to go to metathesis now. I'm sorry? Acid-base. So metathesis, we have AB, right? A is H+. So what anions does H+ react with? H+ likes to react with basic anions. When I say basic, I mean their base. Stronger than what? That's for redox. This is a bit tricky because this is actually HF. And so we talked about it. C1. If we think about fluoride, that brings up a question mark here, because we know this. We know chlorides, bromides, and iodides are soluble, except for which ones? Silver, lead, and mercury. Mercury 1, lead 2. But what about fluorides? Was that just a typographical omission, or was that an intentional omission? And the answer is it was intentional. Fluorides are excluded from here. Fluorides have many more exceptions. Can somebody think of why fluoride would have many more exceptions? This is fluoride salts. Have many more exceptions because fluoride is more reactive. Why would fluoride be more reactive? It's smaller, exactly. Fluoride is more reactive since it is smaller. Than chloride. And so what we have to do is we have to consult a reference book. Or Wikipedia. Wikipedia is not a reliable source because Wikipedia, people could put in their own political viewpoints or opinions or whatever. But a lot of the physical properties of the compounds are reliable. They aren't as reliable as reference books because reference books are checked every year to make sure that they have the latest data. But I think we can use Wikipedia for something like this. So let's say we're interested, will calcium fluoride precipitate? And so an example would be calcium fluoride. I know calcium chloride is not one of the exceptions. So calcium chloride is soluble, calcium bromide is soluble, calcium iodide is soluble. But is calcium fluoride soluble? Maybe not, because fluoride is smaller and more reactive. And so what we can do is we can just check Wikipedia and see what it says here. So this is the Wikipedia entry for calcium fluoride. And we have the solubility data here. At 20 degrees C, the solubility is 0.016 grams per liter. And so if it's 0.016 grams per liter, does that mean it's soluble? We can dissolve 16 milligrams in a liter. Would you consider that soluble, slightly soluble, or insoluble? What's the cutoff? Somebody remind me what the cutoff is between soluble and insoluble. No, it's not. If it's basically zero, then a lot of things are soluble. Most everything is. No, there's a cutoff. It's arbitrary cutoff. What was the cutoff? 0.1 moles. And so this is written in different units. This is 0.016 grams. So let me convert that into moles. And so I need the molar mass. Well, calcium fluoride's molar mass is here on Wikipedia as well. So 0.016, let me find calcium fluoride's molar mass. Here. So I'm going to go 0.016 divided by 78.075 grams per mole. And that gives me, oh, come on, 0.016 divided by 78.075. 0.0002 moles per liter. 0.0002 moles per liter, we consider it insoluble. 000 is 0.2 millimoles. It's supposed to be at least 100 millimoles. And so, based on Wikipedia, this is insoluble. And therefore, if there's any calcium around, fluoride would love to precipitate with it. Does that make sense? And therefore, and thus we can look for other things that fluoride will react with, like precipitate, or maybe form a gas, or go from stronger to weaker acid. You know, here, stronger to weaker. Stronger is HF. Weaker is. This would be driving force. All right, any questions on this?